Hello and welcome to Quantum Mechanics Made Easy Beginner Problem Playlist. In this presentation, I'll solve some beginning problems related to Heisenberg's uncertainty principle. My name is Dr. Jacob Hudas. In the beginning problem playlist, I will solve quantum mechanic problems that don't involve pages of algebra. The uncertainty principle tells us that the uncertainty in the position of a particle multiplied by the uncertainty in its momentum has to be greater than or equal to h bar over 2. In classical physics, we need the coordinates at time t equals 0, x of 0, and v of 0. If we know these, then we can get x and v at any time in the future, assuming that we know the forces that are acting on the particle, or we know the energy like the Lagrangian or the Hamiltonian. In quantum mechanics, we need the wave function at time equals 0. Uncertainty is built into the wave function from the beginning. Uncertainty is not related to the measurement. The uncertainty does not arise from the measurement. The uncertainty is inherent within the wave function. In quantum mechanics, it's a fact, postulate you can say, that the wavelength of a particle corresponds to its momentum. Here's a wave with a given wavelength, we'll call it wavelength 1. If this were the matter wave of a particle, that particle would have one specific momentum, p1. This wave, lambda 1, corresponds to momentum 1. Lambda 2 has a different wavelength that corresponds to momentum 2. Lambda 3 is a different wavelength that corresponds to momentum 3. In quantum mechanics, wavelength is directly related to momentum. In nature, a particle doesn't come as one single wavelength, as one single momentum value, because if it did that, then you'd know its momentum exactly, and that would mean its position would be spread out through the whole universe, and that's not a physically realistic situation. In nature, what happens is a particle comes in a sum of different momentum states. On this slide, what I have is I have a function y1, and this is a sum of sine waves starting with a k value of -3 and ending with a k value of 5. There's 20 terms in this sum, and the k changes by 8 over 19. I chose to use 20 terms simply because that's the example that I chose to do. When you plot all of these different sine waves together, the plot y1, which is the sum from n equals 1 to 20 of this sine function, is plotted on the bottom of the screen. If delta k were smaller, these little bumps here would become flat. And what you notice is the particle is localized in this region. This is what we call a wave packet. The particle is localized roughly between -3 and +3 on the x-axis. If I were to say, what is the position of the particle? You can't tell me the position of the particle. It's spread out it's spread out over the wave packet between -3 and +3. You could tell me the particle is between -3 and +3. And by the way, over time, this wave packet would be evolving and moving. Now let's discuss the average and standard deviation for the k values related to the function y1. So y1 had k values that ranged from -3 to 5, and they went in steps of 8 over 19. Just to refresh your memory, these were these numbers that were inside the sine functions. And so the average k is equal to the sum of all the k values divided by 20, and that's 0.76. The standard deviation tells you how the k's are spread out. The formula for standard deviation is the square root of 1 over m times the sum of each individual k minus the average k squared. So sigma squared is 1 over 20 times -3 minus 0.76 squared plus minus 2.57 minus 0.76 squared. You add all this up, take the square root, and this is 3.92. The average is 0.76 with plus or minus of 3.92. That's a relatively large spread in k values. Now let's go on to a similar example. I again chose 20 terms to make the two examples similar, but now the k values go from -1 to 4. Before, the k values went from -3 to 5. Now they go from -1 to 4, and so there's a smaller spread in k. If I plot all of these functions, what I get is this function here. Again, if delta k was smaller, this would become more flat. And in quantum mechanics, this is actually a Fourier transform, not a Fourier series, so delta k does become infinitesimally small. I'm just showing this for teaching purposes. And so now what we see is the particle is spread out between -6 and +6. Before, the particle is spread out between -3 and +3. Now it's spread out over a larger range of x values. It's more spread out on the x direction, and we know that the k values are less spread out. The k values are more concentrated. The average value for k is 1.27, and the standard deviation, sigma k, is 2.16, which is a smaller number. This is function y1, and this is function y2. y1 has k values that range from -3 to 5, and so the k values are more spread out, and the position is more concentrated. This function was made up of a sum of 20 sine functions, but those sine functions had k values that range between -3 and 5 in equally spaced units, and that makes a particle that's confined between -3 and +3 on the x-axis. This function was built out of 20 sine waves with k values that range from -1 to 4. It had a smaller standard deviation in k. What that leads to is that this particle is more spread out on the x-axis. If you're more spread out in k, you're less spread out in x. If you're less spread out in k, you're more spread out in x. This picture is the Heisenberg's uncertainty principle. This really does cover the concepts of the Heisenberg uncertainty principle. AcePhysics.org, Math and Physics Tutoring with Dr. Hutis. Now let's move on to example 1. A fundamental principle of quantum mechanics is that particles confined to a specific region cannot be completely at rest even at absolute zero temperature. A confined particle is one restricted to a finite space, similar to an atom in a solid. Such a particle has a minimum non-zero kinetic energy. Consider a particle restricted to a one-dimensional space of width L. Determine the approximate formula for the minimum kinetic energy of the particle. You might want to pause the video because I'm going to go over the solution on the next slide. The Heisenberg uncertainty principle states that the uncertainty in x multiplied by the uncertainty in momentum, which is mv, has to be greater than or equal to h bar over 2. For a particle confined to a region of width L, the uncertainty in x is L. We can't actually see this particle. It's too small. We're dealing with quantum mechanics, and these are really small things. So if I know that the particle is within some location L, the uncertainty in its location is given by L. Therefore, the uncertainty in its momentum is the uncertainty in mv has to be greater than or equal to h bar over 2L. I can then divide both sides by m, and the uncertainty in velocity is h bar over 2ml. Kinetic energy is 1/2 mv squared, but in this case, v is not 0. V is equal to the uncertainty in v, which has to be greater than or equal to h over 2ml, so we'll just plug that in here. So therefore, kinetic energy has to be greater than or equal to 1/2 m times this quantity squared, and simplifying this expression, we have kinetic energy has to be greater than or equal to h bar squared over 8ml squared. The reason you don't see these things in your everyday life is because for large m and large L values, h bar squared is so small that this is 0. This is essentially 0 for the macroscopic scale. If you're interested in math or physics tutoring, please check out my website, AcePhysics.org, for math and physics tutoring with Dr. Hutis. Finally, let's move on to example 2. A proton is traveling in the y direction with a velocity of 4.1 times 10 to the 6 meters per second. That's a little bit quicker than I can run. If we can measure its velocity with an accuracy of 2%, what is the precision with which we can simultaneously determine its position along the y-axis? You may want to pause the video now because I'm going to solve the problem on the next page. So to begin, we determine the momentum of the proton. Momentum is equal to mv, mass of the proton, velocity of the proton, that produces this momentum. 6.85 times 10 to the negative 21. The units of momentum are kilograms meters per second. Momentum units don't get a special name like newtons or joules. I don't know why not. Let's work on that, ladies and gentlemen. Given that the uncertainty in the momentum is 2% of this value, we take 0.02 multiplied by that, and this produces the uncertainty in the momentum of the particle. Now, the Heisenberg uncertainty principle tells us that delta y has to be greater than or equal to h bar over 2. And so we're going to say that delta y is approximately h bar over delta py, and we can plug in these values, and that's equal to 7.66 picometers. This is about my vertical jump on a good day. And so thus, the uncertainty in the proton's position is approximately 7.66 picometers, which corresponds roughly to the size of an atom. Are you in need of a great physics tutor? Dr. Hutis can help. Whether you're preparing for a high school test, AP test, or college exam, let me help you ace it. Are you an eager high school student aiming to get ahead and prepare for college-level physics? Or maybe you're a college student and you want to learn even more advanced physics. Dr. Hutis can help. Visit AcePhysics.org and schedule a lesson today.